So let me start by saying that, a lot of people who worked on this problem for many, many years. So this is a 50-year-old problem. And a lot of advancements have been made, mostly due to the advancements in computer technology. So I have here two pictures. The first shows how in '61, the Japanese were doing vowel recognition, and you used a computer full of, a room full of computers, or whatever these things are. And this is how we do it now, like with a little laptop, and you do a voice command system through that. So there has been a lot of progress. And it's not only because of the computers. The problems that people have been tackling are getting more and more difficult. This is out of the Professor Furui's plenary talk in ICASP. It shows how, we moved from simple tasks of so small vocabulary, voice command, from the 80s, to go all the way to natural conversation transcription and two-way dialogue systems in the 2000, after 2000. So the problems are getting more and more difficult, and our results are getting better and better. This is another historical chart that people like to show to the funding agencies to show that we actually have progress. So what this shows is, again, DARPA has been funding projects in speech since the 80s, and they have regular benchmark tests and evaluations to measure the progress. And the first tasks were very easy and small vocabulary, and you see that the first time you tackle a task, the error rate is high, and then as more years we're working on it, the error rate goes down, and the goal is to bring basically. Okay. I thought this building was modern. Okay, and this intimidates me. To bring the error rate down to.
So we should be intimidated.
Okay, to 10% for all the difficult tasks. Oh, thank you.
So this is 10. Okay, error rate. That's what it is.
This is the error rate, yes. So the interesting thing, when I started working, in switchboard, we were at 50-60% error rate. And now it's actually 12 to 15. So we are close to this point that they were projecting. So what have we done? What have engineers done to actually address this very difficult problem? And even though they haven't solved it completely yet, and there are a lot of new ideas being introduced every day, there is an infrastructure that has been set from actually maybe 30 years ago that has remained pretty much stable. So what is the approach that has been taken? You treat this problem as a noisy channel problem. You have an input, that comes from the speaker's mind, and at the end, you want to predict or give a hypothesis of what is the most likely sentence that was actually produced out of all the sentences in the language. So let's look at this channel a little more detailed. So the first part of this channel is a speech producer. This is the human vocal tract, basically, which is, it consists of 4 basic cavities, like the larynx, the pharynx, the oral cavity, the nasal cavity. And, all this system is, it's basically, all of these components are contributing in producing the speech. So I have a very old clip here that shows how everything moves when speech is produced. Let's see if it plays. 1 second. So you see how everything from the back here, basically.
This is an X-ray image?
This is a sequence of X-rays. I think this thing was from the 70s. Very, very old. I like old stuff. See, all of the stuff move from here. The tongue moves up here, the lips, everything. So the way all these things move, basically what they do is produce, speech, which propagates through the air as a waveform by changing the air pressure changes around the basis vibrating point. And as this signal goes through the air, if you talk to a microphone, these changes in air pressure convert to basically changes in electric voltage, and you can observe the signal. So by looking at the signal, you basically can never tell what was said. Nobody can. But what people have found is that if you take the spectrogram of the signal, which is basically a sequence of very short windows of frequency analysis, right? And you create this thing, then actually you can read this. There are people that get trained to read the spectrogram, and they can understand what speech it represents. So basically, yeah, it's this frequency analysis that is very important to understand what is the underlying signal. So when we extract features from the signal that we want to use to do speech recognition, that is a basic principle. You take the signal, you define a small sliding window, and then for each, you call this like basically a frame, and then for each frame, you extract a feature vector. And this feature vector contains information about the spectral content of the signal. More specifically, a very well, common example of acoustic feature vectors is what we call Mel frequency substral coefficients. Okay, I'm not going to go through all of this in detail. I just wanted to scare you by showing you how much signal processing is being done. Basically, this part here is what defines the MFCCs, what we call Mel frequency substral. There is a discrete Fourier transform. There is a discrete cosine transform, what this is here. And there are some other filters that basically, this filter here, this filter bank, kind of models the way the human auditory system works. And the basic thing out of this is that what you end up is you get the speech signal, you window it, and then you slide the window over. And what you end here is with vectors, right? So what you do, you have 13, actually 12 coefficients, spectral Sebstrom coefficients. You add the energy, and then you have 13. And then you take derivatives and second derivatives, and then you have 39. So this is your observation vector, let's say, at this channel. There are other representations of acoustic features. There's the PLPs that actually are also very common. There have been neural network features, articulatory features. There has been a lot of research on how to actually find the best acoustic representation. But anyway, so this is very old, and I think it's still very widely used. Okay, so what happens to? So this is now the O. The O is the acoustic feature vectors. The last part of this channel problem is basically the decoder. So what we want is, given that we observe these acoustic observations, we want to find the sequence of words that maximize the probability of the words given the observations. So we use Bayes' rule to rewrite this. So why do we use Bayes' rule? Basically, it's very difficult to come up with a predictive model like this, right? So it's easier to break it down into different components. So if you rewrite it like this, then you can ignore the denominator because it's common among among all the hypotheses, right? It's a given signal. So all you end up is with a numerator, which has two components. Here it is again. The first component is actually called the language model, and it's the model that models the source, which is the sequence of words that were thought or were formed at the speaker's brain. And the second component is what we call the acoustic model, and it's actually the likelihood of the source given, the signal given the source, right? So you have these components. And then you have the search term here, which is the decoding step, where you try to find the maximum, you try to find the sequence of words that maximizes this product. Okay, so let's look at each of these components separately. The first is the language model. So why do we need the language model? You could say, let's keep a uniform prior probability over all the sentences in the language. Well, that's not quite right, because sentences are not all equal probable, as you can see here. This makes sense, this doesn't, in most contexts. So the language model is important to actually disambiguate a speech signal that is acoustically confusable, right? And there is an example here of things that, if you just listen to one part, you don't know what it says, but...
Right one.
What does it say? What right one? Right or left? Right? You can have many interpretations, right? So you have to know the whole context to know what it said.
Give me the right one.
Right. Now there is no confusion because you have the whole context, like versus this one.
I'd like to write one.
Very simple example, but it's indicative of why we need the language model. So the language model gives a probability of a sequence of words, right? Give me the right one. What's the probability of that? We can use the chain rule, a basic probability here, to rewrite this as a product of conditional probabilities, right? So are you all familiar with this? Okay. And then, you can write the probability of all the sequence of words as the probability of the first word times the probability of the second given the first, all the way down to the probability of the last word given all the words that precede it. So these kind of terms, they're very long, and it's actually very hard to compute them from data. So typically people make these simplifying assumptions of just using only the last word in the history. So you say basically that the probability of one given everything that preceded is just the probability of one given the last word, one given right. And this is called bigram model. And if you use only the last two words, then it's called the trigram model. And basically the n-gram model is a model that looks at n minus one words in the history, right? And that's the basic stuff. So how you estimate this n-gram probability is the probability of a word given its history. It's just basically the simple estimation is use the empirical frequency on the data. Basically, how many times did the word I follow the previous words given, how many times the previous words happen. This is actually bigram. So how many times the word I followed the word I minus one over how many times the word minus one happened. So this is what's called the maximum likelihood estimate because this maximizes the probability of the training data. Because now many of the bigrams, the sequence of words, would have zero counts in a given training data, we actually, especially if you go to trigrams, you would have even more zeros. You actually don't use exactly this formula, but you smooth over the probability estimates over a different order of n-grams. So, this is the smooth estimate of the trigram probability. Okay, so the n-gram has been used for many years, and it's still, the most standard way of incorporating language model in our problem, but it's not without its problems. So it's clear that it has many deficiencies. So I have here some examples. One example is there are some n-grams that are more frequent than others for no particular reason. For example, Mary's head is a very frequent one. Dimitra's head is very infrequent, just because Dimitra is an infrequent name. But these two words share very common characteristics. It's both names, both female names. So why shouldn't they share the counts? So there is this what we call class language models, where they try to merge the counts from different words to have a more robust estimate of the counts. Another problem that n-grams don't count is the long-range dependencies. You can see here an example. The dog saw the thief entering and barked, right? So barked is very much related to these first words, but the n-gram loses it because it only looks at the last two words. So predicting bark from ending end, it's not really, very good. But if you had the dog here, it would have been good. So there have been many solutions that have been proposed to tackle this problem, like using syntax information, parse trees. People are still working on these kind of problems. Also, there are other problems that people work on in terms of language modeling. For example, how to model unknown words, how to include subword units in the language model so they can tackle languages with very big vocabularies that is due to morphology or inflections. So there are still many open problems in the language model. Still, the regular n-gram is what pretty much everybody still uses. Okay, so let's move to the second part, the acoustic model. So what kind of acoustic model? What is the basic unit? So for the language model, obviously the intuitive unit is the word. But what is for the acoustic model? Can we build a model for every sequence of words? That's intractable, right? There are too many sequences of words, and we would need too many observations for each of them to have a model. So the next step would be to think, can we build a model for each word? Actually, that could happen. In small problems where you have small vocabulary, you could actually have a model for each word. And you would have this model generate a set of observations for each word. But in real big applications where you have many words, you need to go below the word level. You need to go to phone. The phones is the linguistic motivation to go to subword units that are well defined. So here you take, again, write one, and you write it in terms of phonemes, and you have one model for each phoneme generating the observations. And there we can go even kind of below that, because if we look at the spectrogram of the phones, we see, so the first is the spectrogram of the phone A, I think. I, okay. So you see that it's not constant, right? So there are different, distinct regions in there. I mean, maybe not so distinct, but definitely there is some kind of trends. So what people do is they actually use three regions in the range of the phone, and they have three kind of, let's say, models here for each region: the onset, the middle, and the decay. But we actually go even further than that. If we look if you look at the same phone, like this is the phone A, right, in three different words, you see that the spectrum is actually very different in each of these cases. And why is this? Because the context of the neighboring phones affects very much how the specific phone, is actually materialized here. So what people do is, instead of having a model for each phone, they have a model of each phone given the neighboring context. And then you go into triphones. And again, each triphone has, again, three subunits, which is, the different regions in the spectrogram. Now, though, again, we have the problem that we have too many, right? So we went away from the words because we had too many of these models, and now we have, again, too many triphones if we, have one for each possible context. So, there are ways that you can actually tie parameters between them and smooth them so that you overcome this problem. Okay, but I haven't yet said what the model is. So I'm just talking about what the unit of the model is. So remember, again, this sequence of phones and subphones and words, whatever we want this unit to be, is hidden. We don't know it. What we only see is the acoustic observations that get emitted from them. So many years ago, I guess it's in the 70s, early 70s, people saw this problem and related it to a very well-studied sequence of set of models, which is the hidden Markov models. So let me give a very quick overview of the hidden Markov models and see how this relates to the speech problem. So this is a simple example, simple hidden Markov model example. You have three urns. Each urn has some balls in them, blue balls, red balls, green balls. And the sequence generating algorithm is, you basically there is somebody observing what you do. No, I mean, not what you do, but okay. So let me go back. So you go and pick one ball from you pick an urn first. You select an urn based on a random process, and then you take a ball out of it, and then you show it to somebody, right? So the person sees this red ball, and then based on a random process, you move to another urn, or maybe stay in the same one. But basically, you go and select another ball, and then you show it to this person. So this person, all he sees is these balls that you take out, and you show him. And these are your observation sequences, like our acoustic feature vectors are our observation sequences. And the sequence of what urns created it's hidden, right? So there is a correspondence here. And the question is, can we uncover the hidden urns and say what is like the sequence, given the observations that the person observes? Again, let's go and see what are the actually parameters of these models. The parameters is the number of states, which in this case is the number of urns, 1, 2, 3. The number of observations, in this case is again 3. It's red, blue, and green. It's the number of types of observations, I should say, types of observations. And then you have some initial state distribution, and this is the distribution based on which you select the first urn. Let's assume here it's like 1, 0, 0, meaning that you always start with urn 1, right? And then you have a state transition probability distribution. This is what is the numbers here, right? So you have a probability of moving from one urn to the other or staying on the same urn. And all this is represented in these metrics, right? And then you have a probability from each urn to emit a ball, an observation. So for the first one, you know, the probability of the red balls is 3 out of 6, right? The probability of the green is 2 out of 6, and so on, right? So this is the parameters of the HMMs. And a little more formally, so what forms the HMM? So there is an underlying state process, a change state process, which is Markov. And what does it mean is that it follows the Markov's assumption that if you move from one state to the other, then all you need to know is these two states. So the transition probability depends only on these two states. It does not depend on whatever happened before that. So that's the Markov assumption. And then if you emit an observation from one state, then all you need to know is that state. So the probability of observing something given a state does not depend on anything that happened before that, either of the states or the observations. So these are the two underlying assumptions of the model. And these are the parameters. As we said before, it's the state inventory, the vocabulary, the transition probabilities, the out probabilities, and the initial probability vector. Okay, so these models are tools that have been used to handle statistical problems. And when you use them, there are three basic problems that one has to address. The first problem, this kind of theory was formed back in the 60s. And the first problem is the one of evaluation. Like, given an observation sequence, what is the probability of actually observing the sequence? Clearly, if you know the underlying state sequence, it's very easy of how to get this probability based on the Markov assumptions. But the state sequence is hidden. So what you need to do to get the probability of the observation is actually sum over all possible state sequences. And that's not efficient. They're like n to the t, where t is the number of observations you observe, n is the number of states that you have. So these are like too many sequences that you have to consider. There has been an efficient algorithm called forward algorithm that is used to compute the probability efficiently, and it has n squared times t computational expense, what the word is. Okay, so this is based on forming a trellis, which is some kind of a matrix, and then saving some intermediate values in this table. So have you seen this before? You have. So I shouldn't go on this very in detail. Okay, because I have here a trellis, and that may take a while to go through. Okay, so.
Anybody who wants a trellis, say it now. Otherwise, it'll go too fast. Okay, good.
Okay, let's go through the trellis. So again, we observe these balls, right? Red, blue, blue. And so we put this axis here, our observations. And then on this axis here, we have the states that we have. State 1, 2, 3. These are our urns. We start so what we want to get is, and remember, what is our problem? We want to have the probability of observing this sequence. So at the end, we want to have the total probability over all paths that can go through this trellis that produce these observations. So we start by basically saying, what is the probability, of just going to the first urn and producing the first observation? And this is the probability, right? The probability of the first urn times the probability of the red ball given the first urn. And that's 0.5, if you look at this here and, compute the probabilities. And then you store this value at this point here. That's the probability of just going to the first urn and having that observation.
This is because P1 is 1?
P1 is 1, yes. As I said, the initial probability distribution is 1, 0, 0. So you always start with 1. That didn't have to be the case. You could have 0.5, 0.5, 0, or something like that. But for this example, it's 1, 0, 0. So, then you would do the same for the other urns. In this case, the probability is 0, as I said, because this is 0. And then you store these values. Oops, sorry. I went too fast. You store these 0 values here. So now you're at the first column, and you have populated it by the total probability of being at this state and having observed this ball. Right? So this is what you have. And now you want to get another ball. And you want to say, how do I go here then? How do I find the total probability of being at this state, having observed these two things before me? So what you would have to do is say, how do I get here? You either go from here, or from here, or from here. Right? So what you would do is you find the path for each of these, the probability for each of these paths, and you add them up. And that would be your total probability. So let's see how it would go. So, if you move from state 1 to state 1 and produce a blue ball, that's your probability, 0.1. Right? So then you multiply this 0.1 with the probability of actually being originally at this state, and you have the probability of this path, which is 0.05. Okay? So that's the probability of this single path here. But we have other paths that can go here, which is this one. Right? So this transition has a probability, but this state has 0 probability. So this would be 0. It doesn't add anything. And for the same reason, this would be 0 too. Right? So then you add this up, and then you put the total number here, 0.05. Right? So now you end up with a probability of being at this state, at this time, having observed these two balls. And you can do the same for the other states. Again, you have 3 paths that go there. Only these have non-zero probability. So you multiply this by the probability of this transition, and you get the total probability of the state. And you do the same for the one up here. And you again store the total probabilities at this point. And similarly, you move to the last step. You again compute the transition probabilities of moving to this state. You multiply them by the probability of being at the previous state. You add them up, and that's the total probability of being at this state. And you do the same here. You do the same here. Now you end it. And each of the states has a total probability of ending there, having observed all these balls. So what's your total probability? You add them up. So you go up here, you add them up, and that's the number that you get. And that's how you go through the trellis. So these things that you store here are actually called forward probabilities, because it's the total probability of being there, having observed what you have gone so far. Similarly, you can compute the backward probabilities, where you go backwards and, Anyway, let's not go into that, but it's a very similar step. Let's go to the second problem, which is actually, the decoding problem, which is, the search kind of thing. So given that you observe a set of observations, red, blue, blue, the question is, how do we choose the corresponding sequence, which is hidden, that is the most probable to have actually caused this observation? And this is a search problem, so you try to find the sequence that maximizes the probability of observing this given the state sequence. There is a Viterbi algorithm that solves this problem that is a similar trellis as to what we saw before, but now instead of adding up the probabilities at each stage, you just need to choose the maximum. So it's a much easier step, and it's more efficient. It's n times t computations. So again, I'm going to go through this trellis. Now it's faster because we know what it's doing. You again populate it by the probabilities at the starting point. There's nothing to add, right? And then to move at the next stage, you again have these 3 paths that lead here. Now, at this point, you only keep the maximum path, the maximum score path. The rest, you remove. So that's all that you end up with. And the same for the second stage, the same for the third stage. You don't add them up. You just keep the maximum. And then when you move to the third stage of the trellis, you do the same thing. You have 3 paths again, and you choose the maximum one. The rest go away. And this way you populate the Viterbi trellis all the way to the end. And now you have, at the last state, the best path probability of ending to this state. And again, to see how you end, you see which is the maximum of this. And that's your best path till the end, right? So it was this one. So now, once you've reached this and you have this path through the trellis, you can trace it backwards. And that would give you the answer of which states were actually the most probable to have caused this path. So you can see this going backwards as the states becoming green, right? Because there is only one link to each state. So you just take it backwards and you see where it leads. So it was this sequence, 1, 3, 3, that is the most likely sequence to have caused these observations. Okay, so let's go to the third problem, which is learning. So the problem here is, before we assume that we know the model parameters, right? And we try to find probabilities of an observed sequence. So here we say we don't really know the model parameters. We want to find the model parameters that, given a big set of observations, this has to be quite long, how do we adjust the parameters to actually maximize the probability of these observations? Again, this problem has been well formulated. There is this efficient algorithm, forward-backward algorithm, or Baum-Welch algorithm, which is a special case of expectation maximization. And this gives you efficient ways to compute the parameters at every iteration. So I just want to say, so it's forward-backward. It's basically based on this trellis that we saw before. To compute forward probabilities to a state and backward probability to the state, and then it used these probabilities to form the re-estimation formulas for the parameters. Okay, so the algorithm is only guaranteed to give a local maximum. It does not give you the global solution to the problem. But it is guaranteed to increase the probability of the observation at every iteration. So I keep saying iteration, so I need to say that this is actually an iterative algorithm. You don't just get the solution of the parameters in one step. What it does is it starts with an estimate of the parameters, or a guess, let's say, and then you use these parameters to form your trellis, given your observations. And then based on this trellis, what you do is you compute expected counts for the states and the transitions. And I'm not going to go through the formulas in details, but basically this is a snapshot of the trellis. And you can see how, using the total backward probabilities and the total forward probabilities, you can get the probability of a given state transition, right? And then if you add up all the state transitions, you get the expected counts. And basically your estimation formulas are like this. It uses the expected counts to get the new transition probabilities, and it uses expected emission counts to get the new emission probabilities for the states. And the basic idea here is that you iterate. Once you get this, you have your new model parameters, you go back, you rebuild your trellis, you estimate your counts, you get your new formulas here, you update, and you keep going until your model converges, meaning that either it doesn't change much every iteration, or you decide you had too many iterations and you want to stop. That's not convergence, but that's typically what we do. Okay. So an alternative to this is to use Viterbi estimation, where instead of using the forward-backward paths to get the counts, you use only the best path through the trellis. Okay, so that's enough with HMMs. Actually, that was too much. We should go back to the ASR models. See how we apply these HMMs to ASR. So the model for speech is actually a hierarchical one. So we already saw that if we have a speech signal, we extract the feature vectors. We decided that we want to model, we want our HMM model basically to be a triphon model that has 3 states, each for its sepstral segments. So now, how is this used to produce words? This is where you need the pronunciation model. So if you take this kind of finite state grammar that describes the pronunciation of the word, then each of these circles, let's say here, corresponds to a phone, which would be modeled by a triphon model, right? So, okay, so then how do you go to sentences? You take your little word models and you use your language model that gives you probabilities from one word to the other to get your sentence model. One thing missing here is that I haven't told you how you actually, what is the model that you use to predict the feature vectors? It's HMM, but what is the output distributions? We use Gaussian mixture models to basically to give an estimate of the distribution of observations given a state of the model, right? So why do we use Gaussian models, Gaussian mixture models? So the examples that I showed you before were all discrete, like we had balls as observations. So here we have continuous values, feature vectors, right? We have 39-dimensional feature vectors, and each of them has continuous values. So it's a harder problem. You need a complicated model to model it. So Gaussian mixture models have a lot of, let's say, bandwidth. Basically, they can approximate a lot of distributions. But the basic reason we use them is because the estimation formulas for EM algorithm work very nicely if you use this. So this is the Gaussian mixture model. You have a mixture. These are the mixture weights. And each of these is a Gaussian model, which has a mean and a variance. If you use diagonal covariance assumptions, which we typically use, then your variance, which is the matrix, has only the diagonal elements being non-zero. And that's the number of parameters becomes much smaller. So this is what we typically use. There are other approaches to model the emission probabilities. There is vector quantization. We can use single Gaussian models. You don't need to use mixtures. We can use MLPs, but
so Dimitra, just to clarify notation, earlier you had a matrix A for transitions and a matrix B for emissions.
yes.
So this is now replacing the rows of the matrix. So instead of having
This is the emission probability, B.
B, so this Bj is the emission probability of state J.
That's right. The state J to produce observation T. Yeah. Sorry.
And so the small k is the okay.
The small k is the number of mixtures. J still corresponds to the state. So you have k mixtures. Each of them has a mean mj and a variance as sigma j. Okay, so let's go back to try now to build the sentence level HMMs. So as we said before, we start with the triform models that model the Merrill frequency coefficients. We concatenate the triform models according to the pronunciation of the word. The transition probabilities for this concatenation from one triform model to the other are given by the pronunciation model. And then you concatenate the word models together to form the sentences. And there are two cases here, like either for training or for decoding. For training, the sentences are given, right? Because somebody gives you the transcription, so you have only one path of words. And so you don't have probabilities between them. But for decoding, you need to use the language model. I'll show this more in detail later. Let's look at training first. So how do you form your training HMM? You have your transcriptions, this is your words, you have your signal. You take your transcriptions, you take your lexicon, and you convert it to a phonetic sequence. And then for each phone, you have a model, and that's your raw HMM for your input sentence. Right? 9, so it says 9, 4, whatever. And this is your model. So now you take your WAV file, you do your feature extraction, and you have your observations. Now you can form your trellis, right? So on this axis would be your observations, and on this axis would be your states from your HMM model. And you form your whatever trellis, you do your Viterbi, you do your forward-backward algorithms, and you get your something, your parameters. So this is the iteration for training the model. It's again, as I said before, this iterative procedure. You start with initial parameters for the phonetic models. You use the phonetic models and the dictionary to form the word models. You use the transcriptions and the word models to form the sentence HMMs. And then you use the acoustic observations and the sentence HMMs to create the trellis and accumulate your counts. Using your counts, you update your model, go back, and keep reiterating the step here until you converge. Let's go back to decoding now. So as I said before, now for decoding, you don't know what word follows another. You have, let's say, this is a digit grammar, let's say, right? So you have 9 digits, but there's probabilities from going on one to the other. Let's assume it's not uniform, right? So you have your word HMMs as before, but now for going from the end of one word to the beginning of the one word, you need a transition probability. And that probability is provided by the language model. Here it's a probability of 2 given 0. And if you form your trellis, your Viterbi trellis with this language model, you do exactly what you did before. You have basically for each word, that part of the trellis is as we saw it before. But what happens is at the end state of each word now, you need to move to another word. So how do you do that? You use a transition probability that you get from the language model to add the transition from the last state to the first state of that word. So here you go from word 1 to word 1, you have this probability. To go from word 1 to word 2, you have this probability. To go from word 1 to word n, you have this probability. So again, you form your trellis. Okay, so this is, theoretically the algorithm would work exactly the same as the simple HMM case that we saw, except, there are a lot of practical issues like speed. This becomes very slow once you start putting the language model in there. So, yeah, so what do we really do? So this theory of how we should do stuff is there for at least 20 years, and mostly we do that. But there are a lot of practical considerations and changes that have happened over the years. Actually, this part is not it's also theoretical. So basically, for training the models, we no longer just use the maximum likelihood Baum welts, basically. We use discriminative training approaches, which make the models sharper and they basically better model the observations. Another thing is that we don't just use the plain Viterbi, because that's also very slow. We use beam search. A lot of pruning happens, a lot of hiking happens, heuristics and stuff like that, to speed up the search. Well, okay, not all of it is heuristics, but I won't go into details explaining all the details of what we do here. But basically, the underlying problem is that its search has to be really fast so that the systems are usable. Another practical thing is that, remember that formula Bayes rule? You have an acoustic model, a language model, you multiply them together. Well, that's not exactly true either. What you actually do is you weight these two models when you combine them together. Another thing is that when you combine these two models, you can actually use other knowledge sources and incorporate that into your formula to give you the likelihood of ascendance. And also, you can use multiple systems or multiple hypotheses to kind of do a voting scheme to figure out what is the most probable sequence of words. So you don't just use the maximum likelihood path through the Viterbi trellis. So kind of all these go away. Well, no, they don't go away, but they have been augmented. That's the bottom line. So let me talk a little bit about this multipass search. So basically, there are a lot of knowledge sources that we would like to use, but we don't have a very good way of fitting it in this framework of left to right decoding and search, right? So there is this approach where you can create a first pass of a hypothesis, and then you can rescore them with a more complicated knowledge source. As an example of complicated knowledge source, I want to mention, as I talked before, about the parsing level language models. Right, so these have long state dependencies, and they cannot fit into this dynamic programming like the trellis is being formed. Also, there is knowledge of the following words that can help predicting the current word, and that doesn't fit into this left to right decoding. So all these have to incorporate it in the multipass search. There is also other type of knowledge like prosodic information, which we currently do not include in the acoustic models, and we should, maybe. I have an example here that shows how important it is to include it. The same sentence with different prosody means two different things.
What's that on the road ahead? What's that on the road ahead?
Okay, the second one is freaky, but it's reasonable, right? You would just seeing the sequence of words, you would never understand that this is what it says. But the prosody is very, very clear here. So yes, so that's why we want to use multipass search algorithms. Again, this is now the overall architecture. We have our feature extraction algorithms. They're typically more complicated than just plain MFCCs, but this is what we saw here. We have our decoder search that incorporates the acoustic, pronunciation models, and the language models. And what this happens is it ends up producing a first step or a first pass of alternate hypotheses. And what we do is we take these hypotheses and we form a compact representation of them, which we call a word lattice. And then you rescore this word lattice or n-best or whatever of hypotheses. We rescore it with more complicated knowledge sources. And then you get your final hypothesis from here. OK. So yes, so this is an overview of the technologies that currently use speech ASR, basically. These are like the older ones. They use command and control. Like these are simple ones that you can control a computer, by words or sentences, close vocabulary and stuff. You can use dictation, where you can talk to a system and it can write down what you say. And there have been conversational systems that give information services. I'm sure all of you can use it over the phone, some of the systems. They've been around for maybe 10, 15 years. There are transcription systems that you can transcribe, for example, broadcast news, or you can transcribe phone conversations from a calling center. And those are actually, or there are medical transcription systems where, the doctor keeps, talking to the system, and then it keeps its notes automatically. These are also commercially available. Then there are audio search systems, which are starting now to be commercially available, where, given a vast amount of audio data, you want to find out, where the specific topic happened, for example. For that, you may not need to transcribe the whole thing, but you need to be able to identify where these regions are. Or maybe extract information from audio, so you may be looking for an answer to a specific question, like, I don't have a good example. I don't know what happened in that state, that city, a week ago, right? Something like that. And then, you want to find where in the data they talk about that subject and go and find that information. And there are also speech translation systems where you talk and the system transcribes and translates what you say. And I'm going to give you a demo about a system like that we have developed in our lab. Okay, but before I give you the demo, let me tell you a little bit about our lab where I work. So as Sanjeev said, SRI International used to be called Stanford Research Institute. It was founded by Stanford back in '46, long ago. And at some point, it became an independent entity. It's not longer part of Stanford. We just kept the name, and we're called SRI. So its core business is basically research for either government or commercial customers. And it's a non-for-profit organization. So basically, everything we do comes from getting contracts or grants from different people. We don't have a pool of money to say, we want to work on this. Somebody needs to pay us. Yeah, and didn't I mention it's located in Silicon Valley? We've been there long before, SRI has been there long before a lot of the big names of the Silicon Valley formed. Yeah, we have a very expensive real estate. Okay, so the lab, the STAR lab, was formed in '83, 25 years ago, as part of the major funding efforts from DARPA. And currently, there are 25 engineers. We're a very small group. We have linguists, computer science, and language experts. And there have been commercial products that came out of the lab. So many of you probably know Nuance. So that was a spun out of the STAR lab back in '94. And there are other commercial licensing programs that we licensed since then, but none of them is as famous as Nuance. What we work on, basically, we worked on any aspect of speech that people are willing to do research on. So we work on automatic speech recognition, on noise robustness, portability to new languages. These are the most common topics these days. But we also work on speaker recognition stuff, so speaker diarization, speaker identification, also audio-visual speaker identification. There is a cool project where people work on identifying deception, where somebody is saying something that is not true or is actually pretending to be somebody he's not. So people try to identify these cases. And we work on machine translation, both statistical and rule-based. And this is one of our speech translation systems. So this system we developed under a DARPA program that is called TransTAC, Translation Systems for Tactical Use. Okay. So obviously, this was funded out of the need from the war in Iraq. So people needed to be able to communicate with people, and there is a need for translators, basically, and translators, it's dangerous for them to be collaborating or to be going out in the field. So they wanted a system that the soldiers could carry, and or the medical officers, actually. This was started first. It was developed for medical kind of activities that can communicate with the person and get information back. We've been working on it. It says 2 years. No, it's 3 years actually. And okay, let me try to give you the demo. This has the same problem that the font is not right. I need to make it smaller. I had this open because it takes some time to initialize. So.
Why don't you reinitialize it and maybe people have questions they can ask you while it's...
Well, there is a problem with initializing it again. It's the fact that I've talked to it for a while, and that had adapted a little bit to my voice, which is not a very good voice to talk to a system. So, okay, let me give you the demo, then initialize it, and then somebody else talks to it.
So it's used to a US military guy voice.
Yes, very much so. Yeah. Okay, let's hope this works. Again, yeah, this works better if it's American English. So, okay, let me tell you what this is. Okay, so basically you can talk to it in English and in Arabic, and it transcribes both languages, and then it translates them. So you hear the translation, so there is an audio translation, but you also can see the transcription. Not that you understand the Arabic transcription, but you can see the English. It also plays back the recognized speech, I think. I'm not sure if I've set this option. Okay, so let me just see how this would work. Oh, wait, I need my speaker.
Anyone who speaks Arabic? Yeah. Ah,
Hey,
great.
you can talk to the system, but Iraqi Arabic. We are very specific here.
No Moroccan.
No, I'm sure it recognizes a lot of standard Arabic too, but not everything. There is this noise here. Hello, how are you today?
مرحبا شلونك انت اليوم؟
Okay, so as you see, okay, what did it say?
مرحبا شلونك انت اليوم؟
So is it bad?
No, it's correct.
Okay. Okay, if it's very bad, don't say it. Okay.
By the way, does it matter whether you're saying it to a man or a woman? Would you say it differently?
Sorry?
If the same sentence, would you say it differently to a man versus a woman?
No, it's the same thing.
It's the same thing. Okay.
Yeah, there is an option in the system, but I'm not sure what it does, that it's supposed to be extra politeness. And it's supposed to be used when you talk to women. Okay, the thing is the system is combining for translation a rule-based system and a statistical system. So for rule-based, you can have this kind of rules, right? So, you know, I have different answers for, you know, if you're talking to a different person. But the statistical system, basically, it's the same.
It is the power of the Arabic dialect, because in my dialect, we talk to the woman as a guy. And the like Tunisian dialect, we speak to the guy as a woman. Like there are sometimes different.
So I'm going to try to say something in Arabic. Don't laugh. Okay, so the guy said, hello, how are you today? Okay, the guy will say, Zen Slonik. It's not collaborating. What happened to you? Abort.
Aborted.
Zen Slonik. Oh, come on. This worked before. Maybe I should stick to English. Let me try something else.
Aborted.
زي حوالك I think.
Huh?
How are you? زي حوالك.
I have no idea. Huale? I say Slonik.
حوالك. زي حوالك.
Slonik. So for some reason the Arabic thing is not working. It worked at the hotel this morning. Am I doing something?
Let's Najim try.
Let's try.
Hi. Yeah, this always happens. Yeah. No, it should be okay. It should be working. It's not working. me say something.
Aborted.
Maybe I should restart the whole thing. Okay, let's see. What is your name?
شوف شو اسمك؟
What is your name?
شو اسمك؟
Abdullah? Yeah. Simply, I think I need to restart it. The Arabic part is not working for some reason. Let's stick to English. Have you taken your medication?
هل ماخذ دواء؟
Do you have any fever?
هل عندك أي سخونة؟
When was the last time you ate?
شو وقت أكلت آخر مرة؟
Okay, I don't know. So people can talk to it, but I will try to restart it and see if I can make the Arabic work because it was working earlier. I must have done something.
Yeah, let's give it a try. Restart it and see.
Yeah. Yes. And I practice all these Arabic sentences to say. Okay. One thing could be that I have too many things open. So it's supposed to run on a 4 gig machine, on a 4 gig laptop. So we have these tough books. So this machine has only 2 gig.
You have these what?
Tough books.
I see. What
Yeah.
are those?
It's Sony, no?
Panasonic.
Oh, I see.
Panasonic.
These are not like
Thank
some
you.
military laptop that you
No,
can
no,
drop
no.
from a plane.
So no, these are commercial stuff. They have a lot of memory and they call tough books because you can probably drop it down and it won't break, or you can, I don't know, it can fall in water if it's waterproof and stuff like that. Yeah, 4 gig is not a lot of memory these days, so a lot of computers have it, but this one has only 2. So basically, I wasn't sure if it could run Word and this one at the same time, but it seems that in memory it's okay. So, okay. Do you have any questions about the presentation? Because I'm going to close it now. Yeah.
When does like speech recognition grammars come in? Into you had like this overview model of current recognizers.
Uh-huh.
Are they still used, or is that kind of a dying breed?
Which ones?
Are recognition grammars still used? For example, in the demo that you had,
The language model, you mean?
just an underlying grammar that kind of restricts your search
Oh, I
space.
see. Okay, I see what you're saying. Yeah, I didn't talk about these grammars. I went to the statistical models only. So yes, there are systems that use these grammars. So, for example, these information services, that are online, they have very strong grammars. So you can only say things, a certain number of ways. And for example, if you're using a digit problem, right? You have like 1, 2, 3, 4, whatever. You can have a very constrained grammar. Like, what can you say? It's only these 7 words.
I'll talk a little bit about this in the next lecture.
Okay.
So,
But the thing is that in these, bigger bandwidth systems that need to handle lots and lots of data, for example, broadcast news, transcriptions, these kind of things, grammars are not, strong enough to handle this. So you really need statistical models. So there is also a hybrid between handmade grammars and statistical statistical probabilities within these grammars. So I think you're going to talk about this in the FSMs, right?
yeah.
So you'll see some more of this. Other questions? Presentation done.
So a background buzz, is there any way we can get rid of that?
I don't know. I don't know where it's coming from.
I don't know either, and I'm wondering if that's the reason why it doesn't recognize things.
Well, the English works, so I'm hoping that that's not bad enough.
No. The thing is the English, so that's the thing. So the English is a better model, right? So even if it's bad conditions and noisy conditions, it would still work decently. So the Arabic data that we have is much less.
No, the noise went away. There's something about
Yeah.
the screen. If you make the screen come alive.
I see.
Sorry, no.
Yeah, so because of, because the model is less strong, it gets affected more by, not perfect conditions, like me speaking to it. But that shouldn't be the problem. I mean, it should at least recognize yes and no. La.
No.
There you go. He.
Yes.
Okay, let me try this again. Hello, how are you today? Now the English would work. Okay.
مرحبا شلونك انت اليوم؟
So I wanted to
Great.
say, you see when it starts transcribing that the words change, right? So I say something at the beginning, it says something very weird, right? No or something. So the way this works is it's a multi-pass system. So the first pass is a very small bigram because we need the search to be very fast. So it's a small bigram, and then when it produces the lattice, we score it with a better foreground, very like a strong language model. And that fixes a lot of the errors and it gives you the final result. So that's why you see all these differences. And also on the left here, right, you see the multiple hypotheses that the system produces. So in some cases, these are very different, not here. But basically, the idea is that sometimes you cannot get the system to recognize exactly what you say, but it could be in these multiple hypotheses. So you can just push F1 to F4 and just translate that. Okay. So what would the other guy say? Let me try to get the answer. Zen, Slovak.
Okay, how are you?
What is your name?
شو اسمك؟
Abdullah.
Abdullah.
Do you have any pain today?
هل عندك أي ألم اليوم؟
La.
No.
Have you taken your medication?
شلون بتاخذ دواء؟
E. So that's where my Arabic goes, okay? When was the last time you ate?
شو وقت أكلت آخر مرة؟
Al-Barhat Balil.
This after that you
Didn't get
want.
it. How did I say it very badly? Al-Barhat Balil.
Yesterday at night.
Okay, you can go home now.
زين شو بدك تروح البيت هسه؟
Shukran.
Thank you.
Have a nice day.
مع السلامة.
Alaikum assalam.
Peace be upon you.
So you want to come and talk to it? These are all the sentences I know. So the English vocabulary is, I think, 25.
Can you repeat the question? I didn't hear.
How big is the vocabulary? The English vocabulary is around 25,000 words. It's a limited domain. So it covers, as I said, mostly medical, like questions about have you been here, have you been there, this kind of stuff. But it's pretty big, for English. For Arabic, it's actually bigger because Arabic has this, it's an inflectional language. So for every word form, you have to include multiple versions of it. So I don't remember right now how much Arabic is. I think it's 45,000 right now. So basically, ideally, you would want an English speaker to speak to it for English and an Arabic to speak for Arabic, but I only have one.
I have not Iraqi, so there are many dialects. I don't speak the English part. Iraqi dialect.
Eric can do the English part.
Eric can do the English part. Great. We'll have a real conversation.
Say,
as a New Yorker.
say a couple of simple sentences first so that it can adapt to your voice.
Okay.
Because right now it's adapted to mine.
Are there
So, okay, let me tell you. So to talk Arabic, you push I and hold it down. And to talk English, you push E and hold it down.
And you talk while it is down and you
Yes,
let
and
go,
you
it stops.
release it. So it's a push to talk thing, and then you release it.
Push to talk.
No.
Animals recognition.
You have to keep it pushed while you're talking.
مرحبا بكم.
Welcome to you.
Very nice.
Yes, correct.
No, you have to keep it pushed.
زي حوالك اليوم.
That's almost every day.
That's what you said?
Not really.
I was surprised. how much of the thing is easier what you said in the end best?
I speak ازاي حوالي في اليوم.
So it's the 4 one?
Yeah, no.
This I transferred today.
That's not what you said at all. So the thing is, there are two
Normally-
places where you can do wrong. Okay, so
Yeah.
the ASR can mess up or the translation can mess up. Often both mess up.
It's only the first word here, the F1. The first one is not
Oh,
correct.
the first one. Okay, in
Second
that case, you
one.
should try to say it again.
How are you today?
You want to push E?
Okay, I'm trying.
You have to push E.
Okay. Where do you come from? See, I'm a sheep, so.
We're going to be passing it around.
Yeah.
Okay,
Najim, say where you come from. Let's have a real conversation. See how it goes.
I'll push it.
جيت من العراق.
I came from
Let's
West.
try it. Okay, basic thing, try not to hesitate. Don't have these fluencies, okay? Let's try it again.
جيت من العراق.
Slightly quieter voice may work better.
Okay, neither on.
Well, close enough, but
جيت من العراق.
I came from Iraq.
okay. Three times it. Okay, we can stop this. If you guys want, you can try and talk to it.
Why
But
don't we let somebody else come play?
Yes.
Okay. All right.
Who wants
Anyone
to
else
talk
wants to play?
nobody wants to.
Somebody free.
Come on, it's fun.
All right. Well, here's what we can do. We can formally end the lecture. That way people won't feel under the spotlight. But then they can come over and look.
Come.
Does it have something for handling disfluencies or like?
Yeah, it should, especially for English. But the thing with these fluencies is that all our models don't model them very well. Because this is, again, something that interrupts speech, right? So our models learn whatever is kind of frequent, right? So some of the disfluencies it will handle, for example. I don't know. What do you want? So it removes them, right? There is no reason to translate it, so it removes it.
So the arm went away.
Yeah, the arm went away. I think I want to. The second one is more correct, right? So ideally, you would like to remove the disfluencies, but if you put word fragments, for example, it may mess it up, right? Because it doesn't know exactly what to output for it. And translation really does not work well with disfluencies. So the translation people basically they take the data that may have disfluencies, they remove all the disfluencies, and they learn from the clean data. So that's the answer.
Any other questions?
Does it use this demo? Do you use triphones or all-board models?
Triphones.
Triphones. And how many models?
How many mixtures?
It's okay if you don't remember.
Yeah, I should know that. I wrote a report the other day. 128 times. No, I don't remember. It's a pretty big model, actually.
I can figure it out.
Yeah, but I think it's 120,000 or something like that. It's more than 100,000 for each language.
But I
Okay,
guess
total, you're talking about
Total.
I guess one question is in a domain like this, like you ask the guy, what is your name, right? And so, of course, you don't know what name is going to come back at you. So how will it work? I mean, will it recognize?
So names is an important part of our evaluation.
Okay.
And there are many problems for names. So one is that there are a lot of them that is out of vocabulary. So you cannot really include all possible names in your lexicon and build your models for them. So we have some approaches that are not included in this demo actually, to go to subword units and to produce some subword units, and then this form. So you have this, you can do this in an FSM kind of thing, right? So you can have a flexible grammar that can model names, and that's like a single word, and it can produce many different names. And that's how you include it in the system, so that you can model unknown words.
Okay.
But basically, the biggest problem is that there are many words in Arabic that are both names and words.
Mm-hmm.
So a name of a flower, right, or beauty or something. I mean, a lot of these things are also names. So if somebody says something and then you translate it as, the word, then that's a big error. Well, I don't know why it's such a big error, but apparently it's a big error for those who are interested in it. Because one of the reasons they want to use it is to actually, keep track of people that pass through I don't know, medical place or something like that, right? So you keep this, instead of having a real language speaker, sitting there and writing down everybody's name, you have them going through the system and then you process their information automatically. So if instead of transcribing the name, even transcribe it wrong, like if it's Abdullah, say Abdul or something, but if you say, peace or something, it's not very good. So, but the thing is, as you said, if you say, what is your name? The important part is to transfer that information across to the other person so that he can say something. And then when you hear him say, you assume it's a name. But
do you want to give the subword thing a try? We'll try my name and see what it does.
No, that won't work because it's not part of this.
It's
it needs a bigger memory to run this.
Okay, then it'll be.
Let's say. It will produce another word, that's what it'll do. My name is Dimitra. So what this would do is that we have a post-process tool, right? So when it identifies my name is, and there's something next to it that doesn't make sense, right? You get these phone sequences out of it and you try to form a new word. Let's think of it that way. That's not exactly what we do, but it's a good approximation. So here, yes, we don't have this. It's not running.
And since it's for medical stuff, are there medical terms in your vocabulary?
Yes, there are. Things I don't know, IV and different type of drugs and I don't know. Did you use IV? Say something else medical. I don't know. I wonder if Tylenol is in there.
Tylenol.
Did you take Tylenol? No, I don't think so. There must be some specific medication stuff.
Other question?
I guess in your presentation you briefly mentioned some heuristics for speeding up search. Can you talk a little bit about those?
Talk a little bit about those. So, one of the things is that you do pruning. So basically, when you build this trellis, right, not all hypotheses are active at every point. The ones, so if you take one stage in the trellis, like for a given observation, let's say, some of the paths are low probability. And then you say at this point that this will never recover. There is no reason to keep them all the way to the end. So this is called kind of beam search, something like that. Another thing is that when you build the word HMM, you use a tree structure. And that speeds up the search a lot. Because then a lot of things can be combined at different points. This is kind of hard to explain, like just talking about it. I should have a picture.
If you have caterpillar and catapult, for example, all those words.
It's a prefix tree, so that
it's a
words
prefix
begin
tree
with the same sounds.
Right. So the words share the same sequence of the states, right, until they reach to a point that they diverge. Say it again.
Cat, catapult, and caterpillar.
Caterpillar and catapult. So these share the same beginning, right, and they diverge after a point. So this way you have much less sequences in your trellis in the vertical axis, and that speeds up things. Let's see. Yeah, I guess a lot of these are pruning. So pruning doesn't happen only at each stage. It happens at many different levels. It happens within words. It happens at the end of words. You just try to, maybe there is also this look-ahead pruning, where you try to predict which of these paths can survive. And then, keep only those and kill the rest. You just need to do this faster. So I guess pruning is a big part of it. You cannot afford to keep all paths active.
So as I understand, you use static approach. So you first build the recognition network, static recognition network, and then you search within the network, or do you build it dynamically from the language model?
No, it's actually static.
Static, okay.
I'm not sure about that, but I think there are approaches that use a dynamic language model. They're not as efficient, I think, in terms of speed. So most people, what they do is they take the original grammar, and what they call is, you'll talk about these approaches of determination minimization, so they try to make it as compact as possible. So you take this big language model, HMM, that comes from connecting all the words to each other, right? And then under them there are the triphones and stuff like that. And then you try to make it compact, you know, and then you have the static thing, and then you go through it. But there are cases where you can dynamically modify the transition probabilities between words, for example, for language model. So you can do that.
You might often want to do that in a second pass.
Yeah.
So you go and use static stuff for the first pass.
Yeah, I was going to say that the second pass is a way of doing this efficiently, because in the first pass things become very slow if you try to do this. We have tried to do this, many people have tried to do this for complicated language models that you really want to see their impact on the first pass, you know, without getting lattices, and things become slow.
For instance, HD code from the Cambridge HDK tool, it's dynamic decoder, so you can.
Really?
But I think it's not a real time thing. So you just,
HD code is
it's good.
dynamic. Huh?
HD code.
Yeah, okay. I haven't worked with HDK for many years. Sorry.
No, when she was here, she was at local HDK.
That's 9 years ago. So yeah, I didn't remember that, but yeah, it's doable.
Do you use some heuristics for the states of the HMM, so that you know, for instance, that certain states can survive? Those states that can survive at the same time are grouped together so that they can be evaluated more efficiently, or is it just
those states that can survive?
Because when you do some pruning, then some of the states they die, right? They die out. So those who survive that, you might do some. You might want to do some heuristics, or something like that. So you group them sort of together and you evaluate them at one time, so that it's maybe more.
You do things like that, both for the states. I think this tree representation might be falling into this category, right? So things that, you know, have the same history, you keep them all together, right? And but there are other things that happen. I think what you say also fits into the Gaussian pruning. So again, you have these Gaussian mixture models, and there are many of them. And often you don't need to compute all of them. You make the computation faster by, well, there are these ways that you keep some kind of a hash table of what kind of mixtures are active for given space of acoustics, let's say, right? And if you are in this space, then you don't need to compute everything. You just need to compute only those Gaussians. And so that speeds up things also. So that, as I said, this pruning happens at many levels, you know, including the lower level of Gaussian computation.
So let's continue the questions informally. Let's call the lecture to an end, so that those who want a break can have a break, and others who want to talk to Dimitra can continue talking.
Or you can talk to this without everybody listening to you.
Let's thank our speaker again.